Hi and welcome to this Leaving Certificate Applied Maths video. Today we're looking at vertical circular motion. So in this video, we're going to focus on the key concepts of vertical circular motion. We're going to understand that step-by-step process. And I suppose unlike horizontal circular motion, we have forces acting up, down, and left, right, because the movement in a vertical circle has movement up, down, and left and right. So we need to understand how to approach it. So we're going to look at questions related to particles on strings. We're going to look at questions related to particles on smooth spheres or hemispheres. And hopefully by the end of it, you understand that actually the approach to all these questions is exactly the same. So we're going to look at the role of gravitational potential energy and kinetic energy and how we do these questions, and look at how we deal with ideas of changing tension and changing reactional forces as we're working through. Really, this video is building on horizontal circular motion, and I have two videos already up looking at those. There's an introduction video and then a deeper, higher level video. Both of those will be worth looking at before you work on vertical circular motion. This video is going to look at a few different types of questions. Some are going to come from the ordinary level papers and some the higher level papers. These is the list of questions that we're going to look at in this video. You'll notice we start with some ordinary level questions. The SEC sample paper, it was an ordinary level paper. That gives us a nice introduction to vertical circular motion to understand why we do what we do. We then have a nice question from the exam craft mock paper from 2024, and then we look at the vertical circular motion questions we've had to date with the 2023 deferred and the 2024 paper. I've also brought in a question from the old course, which was the 2020, which gives us a nice question that we haven't really seen tested yet. So when we work with any kind of circular motion, our main page is page 51 in the Formula and Tables book. It's called Motion in a Circle, and we can see the list of formula we have there. We have 5. Our main one, I suppose, we work with is that centripetal force. We have 2 formulas for that, m or omega squared and mv squared over r. The additional formula that we need for vertical circular motion, it's going to be related to energy. And we have potential energy formula. Remember, that's gravitational potential energy, not to be confused with what we work with Hooke's law. And then we have kinetic energy, and then we have the conservation of energy as well. So that's all page 55. So let's work with the 2022 ordinary level SEC sample paper. This is question 1 part B. And it's something I suppose you probably have already seen, but it's nice to bring the circular motion element into it. So a small smooth sphere of 2 kg is connected by a light inextensible string of length 3 meters to a fixed point P. The sphere is held at position A, where the taut string makes an angle of 40 degrees to the vertical, as shown in the diagram. The sphere is released from rest. So part 1 tells us the motion of the sphere may be modeled using the principal conservation of energy. Using this model, calculate the speed of the sphere as it passes through position B when the string is vertical. So we're looking at 2 different positions. It starts here at A and it moves down towards B. So using that principal conservation of energy, we can think of the total energy, so combining our potential energy and kinetic energy at position 1. And I'm going to call that a half u squared, so the initial speed, plus mgh1, so the first height, should then be equal to the total energy at position 2, or position B in this question, which is a half mv squared, so our final velocity, and mgh2, and they are going to be equal. So that is our conservation of energy. And we think of all the information that we have to fill in here. So we're told that the sphere released from rest, which means we know that that u is going to be 0. We know that B is its lowest point, so we can think of that B as being at a height of 0. So it's the lowest point possible on the string. We're looking for V, meaning really the only bit of information that we don't have that we need to fill in for this equation is H1, the height of position 1. So that is our A. So how we're going to work with that is we're going to think about our basic trigonometry. I'm going to put in a horizontal line from A that is perpendicular to the string from position B. So I can make a little right angle there. And I know that the length of my string is 3 meters. So what I have here is a little right angle triangle, and I can work out the side on the right hand side, this one here that I've labeled X, and that is 3 cos 40. So that's a little bit of our resolving. We can use cos and rearrange it, but effectively what we're saying is that side is adjacent, so that is 3 times cos of 40. Now, how that helps us is because if we think of the lowest point through the center of the sphere, I'm doing everything through the center, but it's absolutely fine to think at the top. It's not going to affect your question, how you draw this in. But what we're looking for is this height here that I've shown in green. Now remember that that string can't change length. So that total string is still 3. So if we have 3 and we take away x, which is 3 cos 40, we get a height there of 3 minus 3 cos 40, which is equivalent to the height at position 1. So we're using that triangle to figure it out. That is 0.7. There's a few more decimal places, but I'm just going to round it to 1. And now we can fill in all that information we have. So remember, U is 0 because the sphere is released from rest. We now know H1 is 0.7 meters. We're looking for the speed as it passes through B. So we're looking for V, and H2 is that lowest height, so it's going to be 0. Our mass of the sphere is 2, but anytime we're working with the conservation of energy, especially with higher level questions, that m will just divide out. So we get a half times 2 times 0 squared plus 2 times 9.8 times 0.7 plus a half times 2 times v squared plus 2 times 9.8 times 0. So these two bits effectively are going to go to 0, and we can then rearrange. Well, we don't actually need a lot of rearranging. We can calculate that left-hand side. On the right-hand side, we get a half by 2 by v squared. So that is just v squared. So calculating that out, we get 13.72. And that gives us a v of 3.7 meters per second. So a really nice, straightforward question, but it did have that little bit of trig involved. So part 2, calculate the centripetal force on the sphere as it passes through B. So it's really important we understand where we're talking about. So we're talking about B. So the first thing we'll do is we'll look at the forces that are acting on B. So here is my little sphere at B. Its weight is acting straight down, and then it has tension acting straight up. So one of the key mistakes you can make here is by saying, oh, tension must equal weight. However, that is not true. And that is so important to understand for everything we're doing in this video. Because of the way that this sphere is swinging, it is effectively swinging in an arc of a vertical circle, meaning the acceleration is towards the center of the circle. So there is an acceleration towards P. P is acting as the center of that circle. So there is my P right there. So it's moving towards the middle, meaning, and this is just at B. If we were looking at A, just at A, the acceleration would be like that. But for us at B, because the string is vertical, the acceleration is straight up. The acceleration is vertical. But what this means is because the acceleration is not 0, because there is an acceleration, tension does not equal weight. So you have to be very, very careful. So I'm going to focus on what they've asked us, and that is the centripetal force. So when we're working with any kind of centripetal force, we're asked two things. So what force is acting as the centripetal force? I'm going to leave that question for a second because we're going to deal with it in part 3. And I'm going to focus instead on question 2, which is which formula should we use and why? And here are our options. And the answer is we're going to use this one because we've just worked out in the last question what V is. Okay, we don't know omega, but we do know V. Part 1 asked us to find the speed V at B. So actually, to get the centripetal force, all I'm doing is plugging into this formula. So you might ask, well, why did we draw that diagram at all? Well, it's always good to have a force diagram, and it is not going to go to waste. We just don't need it for this part. So filling in to this formula, we get the mass is 2. Our V from the last part is 3.7 squared. That's all over the radius. The radius of this circle, it is the length of the string, so that's dividing by 3. And we get a centripetal force of about 9.12 newtons. Depending on your rounding and how you approach that and how you approach squaring the square root of the previous answer, you might get something slightly different, but if you're in around 9.1, you are good. So part 3 then asks us to calculate the tension in the string when the sphere passes through B. So this is where we really need to understand what's going on. And this, if you can understand this example, you'll have a very good handle as we move into the rest of vertical circular motion. So what we've just worked out in part 2 is that there is a centripetal force, a force towards the center of the circle with magnitude 9.12 newtons. So that is effectively there. So when I combine tension and weight, I'm going to get that green force there on the left. That is a resultant force. So if we work out the weight first, so weight is mass times gravity, that's 19.6. We can then understand that actually in order to have a resultant force upwards, the tension must be more than weight. And then you have to kind of say, well, how much more? So what we're basically saying is that centripetal force, that resultant is tension take away weight. So in the last part, the first thing on the list that we ask ourselves with centripetal force is like, well, what's acting as the centripetal force? Well, in this question, it is tension minus weight. And the reason we're minusing it is because weight is acting in the opposite direction. Tension will always come first because it's acting in the direction of our centripetal acceleration or centripetal force, and both are going the same direction. So we basically now can say the centripetal force is tension minus weight. Because we've already worked out the centripetal force, we know that's 9.12, and we've already worked out weight, we now get a very simple little equation, which is 9.12 is equal to T minus 19.6, rearranging that, and that gets us a tension is 28.72 newtons. So what you want to think about here is that the tension is first of all overcoming weight, and then it needs an additional force that is going to pull it in a circle. So it has to be more than the weight. So be very, very careful when we have any kind of vertical circular motion. We do have acceleration towards the center, which effectively means no matter what position we're in, there is some up and down movement. This brings us really nicely to how we will approach all of our vertical circular motion questions. So when we're working with them, we have a step-by-step process, the same way we have for horizontal vertical circles. So step 1 is going to be resolving. However, we are going to resolve weight. It is always going to be weight that is resolved. And you want to resolve it in 2 ways: towards or away from the center of the circle and tangential to the circle. So as we're working through questions, really focus on the direction of that centripetal acceleration, because effectively what we're going to be doing is we resolve parallel and perpendicular to that acceleration. Step 2 then, this is where it's different to our horizontal circular motion. We cannot say that force is up equals force is down. That is not true for vertical circles because there is an acceleration up and down because of the way a vertical circle is shaped. What this means is instead we're going to use the conservation of energy. So the conservation of energy is that the kinetic energy plus the potential energy, and that's the gravitational potential energy at position 1, is going to equal the kinetic energy plus the potential energy on position 2. Then step 3 is we're going to look at our centripetal force. This is back to what we're familiar with. Circular motion will always come back to the centripetal force. So that is either using one of our two formulas. Now here's the thing. Because we're working with step 2 and step 3, because we're working with the energy, conservation of energy formula, and then we're working with these two formulas, we will always be solving with a link to V. So V squared is the best thing to isolate from step 2, and then that automatically plugs into step 3, which means the formula that we're going to be using is this one here. Okay, so that's the one we're going to be focusing on. So getting some practice in on these questions, you'll see how it's the same process again and again. Yes, it can be challenging. Yes, sometimes the resolving can be tricky, but you're always working it through the same way. So let's start with a nice ordinary level question, which gives us some numbers, which makes life a little bit easier. So this is from the 2024 Ordinary Level Exam Craft paper, and it's question 10b. So a particle P is released from rest. That's important. On the smooth, so there's no friction, outer surface of a sphere at a height 4/5 above the horizontal plane. So effectively what's happening here, like this is the ground. So it's really a hemisphere. We don't have to like worry about that section there. That part is not important to us. So that's the horizontal plane, that line that I've drawn across. And find in terms of or the height above the plane at which the particle leaves the sphere. So what's going to happen if you think about this is P is going to start moving down and it'll hit some point here. So it'll keep to the circle and then it'll eventually just fall off. So we're trying to find that point. So the first thing we're going to do is we're going to look at the forces acting on P and do some resolving. So here's my P, and I always have weight acting vertically downwards and then a reaction which is perpendicular to the tangent, or another way to think about it is it's along the line of the radius. So if we deal with the sphere, if we were to zoom in, we would end up seeing that at that point it's acting like there is a straight line where the particle is. So think about how on Earth we have that curve, but actually you can feel like you're standing on flat ground. So it's that same idea. So that yellow line is a tangent to the circle and the reaction is perpendicular to that. So then think about where our acceleration is. So our acceleration is always towards the center of the circle. So our acceleration, our centripetal acceleration is moving in here. What this means is we want all of our forces to be parallel or perpendicular to that acceleration. So reaction is fine. It's weight that is the problem. So we need to resolve weight. So let's pull our forces over here so we can work with them. I want parallel and perpendicular to my acceleration, so my weight is going to be resolved in green like this. We need to think in terms of an angle. Now, this question did not give us an angle, so I'm going to put an angle and I'm going to call it alpha and I'm going to put it in there. If you wanted to put it down the bottom left-hand corner of that triangle, that would be absolutely fine. Your numbers will change slightly to mine, but final answer will be the same. So if I take my triangle here and I put on the information the question has given me, so that's or and 4 or over 5, what I effectively have is the adjacent side and the hypotenuse, meaning I can get cos. Cos is 4 over 5 divided by or, which basically just gives us 4 over 5. The ors are going to divide into each other. I can then think about, well, if I have a 4 over 5 for cos, I can then think, well, that must mean it's a 3, 4, 5 triangle. So for my sine, it's 3 over 5. You can do more complicated work with your ors here. So you can do or squared minus 4 over 5 or all to be squared and then work out the opposite and you'll get that number there. But effectively, here is our cos alpha and our sine alpha. And that's going to be helpful for us when we are resolving. So then looking at where my weight is, and in particular where this angle is, it means I can fill alpha into here to help with my resolving. What that means is the one beside it is my adjacent, that's cos, meaning the one here must be sine. So this is my weight, mg sine alpha, and then here we have mg cos alpha. So that's our resolving. You're always resolving your weight. Okay, so its weight is always going to be the one that's an issue here if we need to resolve. So now that we've done our resolving, our next step is to look at the conservation of energy formula, and our focus is finding V squared or isolating V squared. So our conservation of energy is going to be at this position, which is position 1, and there's going to be another position somewhere down the way, which is going to be a position 2, and we don't know how far that is above that horizontal line we've drawn in. That's what we're looking for. So we get a half mu squared plus mgh1 is equal to a half mv squared is equal to mgh2. So think about the information that we have. We were told that the particle is released from rest. That means U equals 0. And it's at a height of 4r over 5. So this is going to give me h1. And then find in terms of or the height above the plane at which the particle leaves the sphere. So I'm looking for h2, but I also don't know v. So what we're getting here is a half times m times 0 squared plus mg 4 over 5 is equal to a half mv squared plus 2mg, and I've just called this height. We're looking for h. You can call it x, you can call it whatever you want. So this first piece disappears. Then what you'll notice is there is an m in each of the terms that we can get rid of. A very common kind of next step for students is to get rid of this half by multiplying everything by 2. However, a common error is not multiplying everything by 2. So just be very careful with that. So multiplying the left-hand side by 2 gives us 8 over 5 GR. You can put 8 over 5 R times G. The order there is not important. Multiplication is commutative, so it doesn't matter what way we write that. And we get something that doesn't look particularly nice. But remember, our focus here is to isolate V. So V squared is going to be 8 over 5 GR minus 2GH. It can be helpful because we're subbing this in and we want to do some cleanup in our next step. It can be helpful to pull out any common factors to the front. So in this case, we have a G that's common, so I've just pulled that in front, and that leaves us G times 8 over 5 or minus 2h. If you want, make life easier for yourself, you can write this as a decimal. It's a nice decimal, so you're welcome to leave it as 1.6 instead of 8.5. So we've now done 2 steps of our process. Step 1, resolve weight. Step 2, conservation of energy and isolate your V squared. You're always going to be isolating your V squared. You don't even need to get V, and you'll see why in a second. Get your V squared on its own. Be very careful not to make assumptions. A very bad, incorrect assumption that can often be made by students is that when a particle leaves the sphere, it has no speed. That is not correct. It does have speed, okay? It does have a v. It won't generally, in a question, ask you where it stops. We won't have that kind of question for a sphere. We can see it in other types, so maybe with tension, but for a sphere, it generally starts from rest and it will still have a speed. So the next thing, this is step 3, we want to look at our centripetal force. Just like with horizontal circles, we're looking at 2 things. What force is acting on this as the centripetal force, and which formula should we use and why? Now, Second question is quite straightforward. That's not going to change. But the first one is a little bit trickier. So we need to always think, well, what is acting as the centripetal force? So remember, here is my acceleration towards the center. Looking at that, that means this direction is positive, this direction is negative. What that means is our centripetal force is mg cos alpha minus my reaction. I'm just going to draw back in my horizontal plane here. So remember, this part of the question doesn't matter, or that part of the sphere doesn't matter. So then the next thing we're looking at is, okay, which formula should we use and why? We've just isolated our v squared, which means we're going to work with this one here. You can now see why we leave it as v squared, because you're not going to square root it just to square it again. It's a waste of energy. Some students even leave the m in there and get mv squared, and that's perfect as well. I kind of prefer to get rid of the m. You'll have to pull it out in front anyway. It's completely up to you. So let's sub in what we know. So our centripetal force, we have agreed that that is mg cos alpha minus the reaction. And that is equal to m times our v squared, which is g times 1.6 r minus 2h, all over r. And then this you really have to be careful here. It's important to show this line to show that we understand what's acting as a centripetal force, and then at this point decide, okay, we know that the particle leaves the sphere, which means that the reaction is going to be zero. So now in this formula, I'm going to let or equal zero. You just don't want to go straight into saying, I'm not going to put the or in. You really want to show that. That's a really important step. It's really important to demonstrate you understand what's going on. I'm plugging in for my cos alpha. You could have done that earlier. My or is zero, so that's now gone. So I get mg 4 over 5 is equal to mg times 1.6 or minus 2h. You have an mg on both sides, which disappear. We can do a little bit of cleanup. So that's 0.8, and I bring my or across from the bottom line. So I get 0.8 or is equal to 1.6 or minus 2h. Remember, we're trying to find in terms of or the height. So I'm trying to get h equals an or, and my answer is absolutely fine. So we get 2h is equal to 1.6 or minus 0.8. 2h is 0.8 or, so h is equal to 0.4 or 2 or over 5. So as vertical circle questions go, this wasn't the trickiest. Although it did have a lot of variables, and they will have a lot of variables, it didn't have as many as we might see in a higher level question. But this is a nice one to kind of start with to get used to the steps for vertical circular motion. This is question 10b from the 2023 higher level paper. A toy car track consists of a series of components that connect to make a closed circuit. Part of the track makes a vertical circular loop. To model the motion of a car on this track, its velocity at the base of the loop, point A, which you can see on that diagram, is expressed as u is equal to the square root of k g or, where or is the radius of the loop, g is the acceleration due to gravity, and k is a constant. This model ignores the effects of friction. Draw a diagram to show the forces acting on the car at the instant when the radius to the car makes an angle theta with the upward vertical. Okay, so what's interesting about this is that the car is going to be inside the track. So if you can picture it, my drawing's not going to be great. So the car is going to come around. So it's going to be inside. So by the time we get to this position, the car is here. And the main takeaway from that is the surface is behind it, meaning reaction is going to go that way. So just be very careful. If it's on the outside, then reaction goes out, but it's inside. So you have to read the question carefully and make sense of it. So here is the particle when it gets to this point here, and let's draw the forces acting on it. So the first force, really simple, is our weight. The second force is reaction, and like I said, that's going to move in towards the center of the circle. It's pushing it away because you can imagine the track is there. So our acceleration is our centripetal acceleration towards the center of the circle. So it's along this line as well. So when we're working with a question like this. So draw the diagram to show the forces. That's it. That's all we have. You've got full marks for that. Be careful if you decide to resolve on the same diagram. Ensure that either the original force is crossed out or the resolving is done in a different color. I think the cleanest thing to do for any circular motion questions is to create another second diagram very quick and resolve on that. So this is our second diagram where we're taking what we had initially and we're just going to resolve our weight. Now, our weight needs to be resolved parallel and perpendicular to the acceleration. So that means we're going to have our green pieces here. So you can see it's going along with reaction and then it's perpendicular to reaction as well. So next we need to focus on our angle. So where are we? So if I put in my vertical just with the dotted line there. So remember, if it helps to use your diagram, do. So here is my particle. And then my reaction is here. So you can see then there's my vertical and there's my angle. So I put that angle in there. So try and mirror what's from your diagram. I'll put that. So try to mirror that on your resolving diagram. So that is theta. So that means we also get a theta in here, which helps us to resolve our weight. So the reason I can put my theta not just here, but also here is because these are alternate. So we have two parallel lines with a diagonal through them. So what that means for us in our resolving is that we get mg sine theta and our mg cos theta. So we have that resolved, which is great. So then the next thing we're going to do, our next step, now that we've got everything resolved, is to look at the conservation of energy, and we're going to focus on getting our v squared. So here's our position 1 and here's our position 2. I find it helpful in a diagram to be very clear about where my two positions are because it's easy to get that confused. Sometimes in vertical circles, we're working from the top down. Sometimes we're working from the bottom up. It really depends on the question. So if we think about what we know happens here, we have our u equals root kgr, so that's going in as our u. H1, it's at the bottom, so our H1 is going to be 0. And then we're looking for our v, so we need to do a little bit of work about what is H2, what's that height at position 2. So I'm just going to remove that reaction I had in there. And our H2 is just going to be this height here that I've put in red. So it's like, well, how do we work that out? Because we don't want to have a v and a h. We're not looking for h. We're looking for, in this part, it's asking us to find cos. But honestly, in a question, you can go through these steps, and then when we hit a certain point, we can look and say, okay, well, what is the question asking us? So the easiest thing to do to figure out this height here is to break the circle in half. So let me put in that halfway line. So like break that circle in half. I'll put it in black. And we know that this part is or, so that's okay. So it's then just the top bit that we care about. So if we put in a little triangle here and bring it down and call that side x, then that height is going to be the radius. So again, let me put in that line. So it's going to be the radius down there plus this x that we're working with there. So that's what effectively we're saying. And again, let's put in our vertical to put in our angle. Let's put our angle there. That allows us to very nicely say, well, x is or cos theta because it's adjacent. You're welcome to use your sine, cos, tan formulas and work through it, but this is something you should be very good at. That should be coming very quickly. It'll speed you up in questions, being able to understand that the adjacent side is always the hypotenuse times the cos of the angle. What that means for us for H2 is we get or cos theta plus or. Which just means we're not adding in extra variables that don't need to be there. So let's fill in what we know. So I'm sorry, I've just pulled out the or here first. When you're subbing in, having common terms pulled out can make it easier, but you don't have to do that. So we get a half m instead of u, we're putting in the square root of kg or, and that's all going to be squared, plus mg, and that's a 0. So this bit here is going to go is equal to half mv squared, and then we have mg or bracket cos theta plus 1. Okay, we're trying to isolate our v, so we have an m in all parts that can be divided out. I have a half in front of my v squared, so I'm going to multiply both sides by 2. Do make sure you do it. So I have a half here and a half here, but I will need to put a 2 in there if I get rid of those halves. And that's a really common error with students forgetting to do that multiplication on the term, on the potential energy term, the term that doesn't have a half. So what we end up with here is kgr, because we've squared the square root, is equal to v squared plus 2g or cos theta plus 1. So I want v, so we end up with something like this. V squared is equal to kg or minus 2g bracket or bracket cos theta plus 1. You're welcome to multiply that out. Sometimes students prefer to do that. But I'm going to do just a little bit of cleanup here up on the right because I've run out of space down there. So v squared is equal to kg or minus, I've just pulled out the or in front as well, so it's 2g or bracket cos theta plus 1. If you want to pull out the g or and do more with it there at that point, you are welcome to. I'm just going to leave it here for the moment. This is what I'm going to use for my substitution. So bear in mind, I haven't actually read part 2 yet. This is a very standard process for any vertical circles. And this can be nice because vertical circle questions are difficult, but often when students read the question, they try to do something different, but our steps are always the same. So you will look at that question in a second, but for now, I'm just focusing on my steps. Step 1, I resolved my weight into the mg cos and mg sine, and then I did my conservation of energy. I'm now on step 3. Step 3 is asking about the centripetal force. So what force is acting as centripetal force and which formula should I use and why? So looking at my resolved weight, my resolved formula or my resolved diagram here, I know everything is moving towards the center. So actually both of my forces, reaction and that component of weight, are helping move it in a circle. So what we have here is going to be our centripetal force is the reaction plus mg cos theta. So the direction here is so important. That's why those diagrams, it's not just about getting your marks on those diagrams. Those diagrams have to work for you. Make sure they're big enough so you can see what's going on. Make sure they're clear enough that you can work on them. It's fine to do a sketch, but make sure they're helpful for you. So then which formula should we use and why? Well, again, we've pulled out a v squared from our last step, so we're going to be using this formula here. Now, you might be questioning, why am I even putting that question up if we're just always going to be using the centripetal force equal to mv squared over r? It's a good question to ask yourself anytime you're doing circular motion. You need to understand that the difference between vertical circles and horizontal circles is the first piece. So with horizontal circles, we say forces up equals forces down. With vertical circles, we do energy, but the rest is the same. The circle bit remains the same. The centripetal force is equal to blah, 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 which one will we use and why. In horizontal circles, it changes, but for vertical circles, we tend to, in all cases, go back to the v squared because that's what we've isolated. So let's start filling in into this formula that gets us or plus mg cos theta is equal to this. Now I'm going to go back and actually read the question. So if the car, this part 2, if the car loses contact with the track at the instant when the radius of the car makes an angle of theta to the upwards vertical, show that cos theta is equal to k minus 2 over 3. If you had read that at the start, you might have gone, I have no idea how to get that. But it's actually about going through the process step by step, and eventually we'll be able to come up with a value for cos. So the big thing for us here is the fact it says the car loses contact. what that means is the reaction is going to go to zero. There will no longer be a reaction. As soon as a particle falls off or a particle loses contact, or is going to be zero, which means we can ignore this or, which takes away one of our variables from this question, which leaves us with this. We can divide across by an mg. We can also divide the ORs into each other here on the right hand side. So we're left with this. And suddenly you might go, oh, now I see where that cause is coming from. Don't overthink these questions. Follow your step-by-step process. Vertical circles are a really great question. They're not attempted by a lot of students, or at least haven't been in the past. Students find them difficult. They are difficult, but when you get that process down and when you're good at that process, there's very little the question can throw at you that you won't be able to do. So let's do a little bit of rearranging here. Be careful. This is the kind of thing that kind of catches really good higher level applied math students. They kind of miss things like multiplying out a bracket with -2 because they're kind of 2 steps ahead in their head. So please do take care with this. We get 3 cos theta is equal to k minus 2. And then we get cos theta is equal to k minus 2 over 3. So actually wasn't a bad question if you know your step-by-step process for vertical circles. This is question 10 from the 2023 deferred higher level paper. A smooth cylinder of sphere 1.5 meters lies on its side in a fixed position on horizontal ground. A diagram of a circular cross-section of the cylinder is shown below. The point of contact of the cylinder with the ground is fixed at point P. A small object of mass m rests on the highest point of the cylinder vertically above P. The object is slightly disturbed from rest. I'm actually going to highlight this because there's quite a lot in this question. So rest so that it begins to slide down the cylinder. When it slides, it makes an angle theta with the vertical as shown in the diagram. Okay, so that was a nice preamble, but basically we see something we're very used to. So a particle was at the top and then it slides, it starts from rest, and the question, we'll look at the actual questions asking us now in a second. Okay, so what's interesting is the idea that this is a cylinder, and you might be looking at going, that's not a cylinder, but if you can imagine like the 3D, we just can't see the back of the cylinder. So sometimes that word be like, oh, we only looked at spheres, or we only looked at maybe other things. So you can look at spheres, maybe hemispheres, but actually a cylinder is going to work exactly the same way. So a student wishes to model the initial motion of the object as motion in a vertical circle. Outline the assumptions made by the student's model. Now there is a lot, and I'm going to go deep into these, but you don't need to. The reason I'm kind of going deeper into this is because it's great from our modeling point of view to truly understand what we mean by assumptions and the kind of things that maybe we don't talk about enough for questions. So first is the fact that there is no friction or air resistance. Here we're talking about a smooth cylinder. Air resistant, we don't deal with air resistance a lot of the time. You might see a little bit come up with differential equations, but in general, when we're dealing with any kind of projectiles or here like in circular motion, we're ignoring that, so it's neglected. Motion is constrained to a circular path. So we're saying that the object remains in contact with the surface of the cylinder as it moves until we're told otherwise. So it's not like bouncing up and down, or it's not like a bumpy surface that even from a frictional point of view we mightn't care about, but that it's like losing contact and coming back or anything like that. Energy conservation. So the only forces doing work on the object are conservative. So what we mean is gravitational force, and the total potential plus kinetic is conserved. That's an assumption. And as the object descends, gravitational potential energy is totally converted into kinetic energy. So all those bits and pieces there. Point mass approximations. This is one, I suppose, again, maybe we don't talk about enough. The object is treated as a point mass, meaning its size and rotational motion is effectively ignored. I suppose this links back to the idea of air resistance. That's why we say, well, there is no air resistance because it's a point mass. So it literally just has mass and nothing else. So we don't have to deal with some complications that we would if we thought about it as something bigger. Because imagine if that was like a tennis ball rolling down a bigger ball and then its rotation itself has to be taken into account. So we simplify this. Remember, assumptions are always to simplify a question for us. And then motion is in a vertical plane. The object moves in two-dimensional plane, no lateral force or horizontal displacement, especially here when it's a cylinder where it could maybe go in a different direction back a little bit or at a diagonal, if you can imagine like a spiral around the cylinder, so that we only focus in a two-dimensional plane here. We can't add in that third dimension. Now, you would not be required to write all of this down for the question. You even wouldn't need to give the explanation. I'm just giving these to you so you can understand that actually a lot of times in a question, we have a lot of assumptions that we've made that we just maybe don't talk about. Because this is such a key element for your modeling project, it's a good little exercise for yourself in a question to think, oh, what are the assumptions made in this question? So getting into the actual meat of this question, the actual numbers, or I suppose the calculation part. Part 2 asks us to calculate the value of theta when the object leaves the surface of the cylinder. So you might be thinking, oh, I'm not sure how I'd even like go about getting a theta. Don't worry about that. Focus on your steps for vertical circular motion. So even though it doesn't ask us this in the question, we will do a force diagram. So here's our particle. And we have weight acting down, and we're doing this at the position we can see in the diagram, which means there's a reactionary force that is along the same line as the radius, but it's working outwards because the surface is underneath the particle, so it's pushing it up effectively. So our acceleration is always towards the center of the circle. So this is our lovely little force diagram. We need for our next steps to have everything, either all our forces parallel or perpendicular to that acceleration, which means we need to resolve our weight. So here is our force diagram, and we're going to resolve our weight showing these green forces here. So you can see it's along the radius and perpendicular there as well. So in terms of an angle, we can put in our vertical. So bear in mind that our green line here, so this one here that I've just scribbled on, is going to be matching here. So they're the same direction. So that means we can use this diagram to help us. Let's put in our vertical line, our theta, which also means that there's a theta here using the idea of alternate angles. This gives us an mg sine theta and an mg cos theta. So then our next step is to look at the conservation of energy, and we're isolating our v squared. So position 1 is the top of the circle where it is, they have a nice language here, so slightly disturbed from rest. So do bear in mind that this starts from rest and then it goes to position 2, which we'll work with at an angle. So here's our formula. Half mu squared plus mgh1 is equal to half mv squared plus mgh2. So we're going to work above the horizontal, which we can see down the bottom of the diagram, meaning the height at position 1 is going to be the diameter. The radius is 1.5, which means that height is going to be 3. So the height then that we're missing is h2. So we need to understand how high is it when it gets to position 2. You can see it there in red. We can break that into a radius plus an extra piece. So imagine we draw our vertical line through here. So we have our radius down there plus our extra piece. In order to get that extra piece, let's look at this triangle. I'll bring it down. We have a radius of 1.5. We have x here. And that means that the height 2 can be written as the radius plus this extra bit x. Don't want to introduce any more variables, so let's work with the angle we have. So we have an angle against that vertical, which means using alternate, we can also put the angle there and rewrite our x as 1.5 cos theta. That gives us a height 2 of 1.5 cos theta plus 1.5. And if you want to pull out that 1.5, we can. So now substituting in the fact that u is 0, h1 is our 6, and our v can be isolated, and h2 is 1.5. our H1, I should draw it on the diagram so we have it. Our H1 is here, and it is the diameter, but the radius is 1.5, so H1 is 3. So that gives us half m times 0 squared plus mg times 3, the diameter, plus a half mv squared, mg 1.5 cos theta plus 1. So let's divide across by an m first to get rid of all of this. Actually, that first piece is completely gone because it has a 0 in there. And then let's get rid of the half in front of our v by multiplying everything by 2. So we end up with 6g is equal to v squared plus 2g 1.5 cos theta plus 1. And let's get v squared on its own. So v squared is equal to 6g minus 2g bracket 1.5 cos theta plus 1. Let's do a little bit of cleanup on that. So 2 times 1.5 gives us that 3g. And I'm going to pull that 3g out in front. That's common, leaving us with 2 minus cos theta minus 1. Watch your signs there. Just be really, really careful with that minus. And it gives us 3g, 1 minus cos theta. You don't have to do all this cleanup now. You can wait. But I've just done it here. So we have our v squared in the simplest form it can be in. So now let's keep going. We have resolved, we have looked at our conservation of energy. So our next step is centripetal force. So what force is acting as a centripetal force? Which formula should we use and why? So our centripetal force in this question is going to be mg cos theta minus our reaction. Because we have a v squared, we're going to use this centripetal force formula. Let's fill this in. Mg cos theta minus or is equal to m bracket 3g bracket 1 minus cos theta all over 1.5. Our reaction, we know that we're talking about theta when the object leaves the surface. This means our reaction is 0, so that reaction disappears. So I've kind of just broken out that 1.5. You can do this kind of whichever way you want, but I'm going to divide across by my mg, and then I can divide that 1.5. Effectively, you can just divide 3 by 1.5 and leave yourself with the 2, whatever way works, and effectively we get this. Cos theta is equal to 2 times 1 minus cos theta, and then multiply that out, get all your causes together, and your cos terms together. That gives us 3 cos theta equals 2, and cos theta is equal to 2 over 3. They wanted the value of theta, so cos inverse of 2 over 3, or 71.85 degrees. So that's our answer to part 2. So part 3 then asks us to calculate the velocity of the object when it leaves the surface of the cylinder. So when it leaves, we know that the velocity squared is 3g times 1 minus cos theta. We know that cos theta is 2 over 3. So actually, we can do some very simple substitution in here and work through. And that gives us a final answer of v is equal to 3.13 meters per second. So finding that velocity as the object leaves the surface of the cylinder is very straightforward. There can be questions which then go a step further and talk about what happens after it leaves the sphere. Remember that the velocity is always tangential to the radius at that point, and then we can work as a projectile if needed. So this is question 6, part B from the 2020 higher level paper. Although this question comes from the old course, this is a great example of when we're dealing with an object on a string. A particle P is attached to one end of a light inextensible string of length d. The other end of the string is attached to a fixed point O. The particle is hanging freely at rest when the string is vertical. The particle is hanging freely at rest when the string is vertical, when it's projected with the speed root 3 gd. So effectively, if you want to kind of put that into your diagram to help you, we have a little bit of sorry, no, my pen. So down here, so that's what we have, root 3 GD, so it's down there. And the particle moves in a vertical circle and it becomes slack at when P is at point B, so we can see that there, and OB makes an angle theta with the upward vertical. Show that cos theta is 1 over 3. Again, do not panic about how am I going to do that. Our focus is on our step by step. So we're going to focus at when we're at B. So when the particle is at B, what forces are acting on it. So at B, we have our weight coming down and we have a tension which is pulling it in, and the acceleration is always towards the center of the circle. We then want to ensure that all our forces are parallel and perpendicular to that acceleration, which means we are resolving our weight so that it is going along the radius and also perpendicular to it. In terms of an angle, we know there's a theta there, which means there's also a theta here. And that gives us mg sine theta and mg cos theta. So now that we've resolved our weight, we're going to look at the conservation of energy. So here's our two positions. Let me just move this out of the way. Root 3GD. So there's our position 1, and then it moves up to B, which is position 2. It's really important you get those, you understand what positions you're working on. In terms of our formula, then, we know our U. Our height at the bottom is going to be 0. We're looking to isolate that V, and we just need to do a little bit of work on H2. So our height at position 2 is this red bit here. We can break that into a radius. So if you think, here's our line. So this bottom bit is just a radius, and then we have a little bit on top. We can use a little right angle triangle to figure that out. There's our triangle. We know the length of the string is D, so that's acting as our radius at this point. So actually I should change this bottom bit to a D. And I'm going to work out this part that is X. This means that I can call H2 the radius, which is D, plus this extra bit X. Going back to that little right angle triangle, I can look at my angle and rewrite X in terms of that angle. So it's D cos theta, meaning H2 can be written as D cos theta plus a D, which allows us to pull out that D in front. D bracket cos theta plus 1 can make it easier when we're working with it, but you do not have to isolate that. Let's sub back into our conservation of energy formula. We have a half m instead of u root 3gd squared plus mg0 is our height one, is equal to a half mv squared. That's what we want to isolate, plus mgd cos theta plus 1. The 0 is gone and we can get rid of the m from all sides. Some students like to leave it as like mv squared, and that's perfect, and plug it in. It's completely up to you. Let's get rid of the half. We have a half here and a half here. So if we get rid of those, you make sure you put your 2 in there. It's a very common error. That gives us 3gd is equal to v squared plus 2gd bracket cos theta plus 1. And I'm rearranging that to get our v squared on its own. You can do a little bit of cleanup with this. You can leave it as is, but you can do a bit of cleanup. So I pulled out a GD in front because it's common, and then you can see we're left with 3 minus 2 cos theta plus 1, and then you can do 3 minus 2 cos theta minus 2, which gives us v squared is equal to GD 1 minus 2 cos theta. So that's our v squared. We then want to go step 3. So step 1, resolve your weight. Step 2, conservation of energy. Step 3, we're looking at centripetal force. So what is the force acting as centripetal force in this question, and which formula should we use and why? So in this question, looking at that resolved diagram, we can see that it's going to be tension plus mg cos theta. They're both acting towards that center of the circle. And the formula we're using is going to be mv squared over r, because we have isolated our v squared in the previous question, or the previous part of the answer. So then what we have is t plus mg cos theta is equal to m gd bracket 1 minus 2 cos theta all over d. In this question, we're told that the string becomes slack when P is at point B, which means our tension is 0. So we can get rid of our tension, and we're left then with mg cos theta. I've just pulled the mgd out in front at 1 minus 2 cos theta. There's an mg on both sides. Let's divide that out. The d on the bottom and the d on the top can divide into each other. Leaves us with cos theta is equal to 1 minus 2 cos theta, which gives us 3 cos theta is equal to 1, or cos theta is equal to a third, which is exactly what they asked us to show. So part 2 then says, in terms of D, find the greatest height of P above B in subsequent motion. This is a really interesting question, and it's an add-on that could be, I suppose, put on any vertical motion question. So when a particle is on a string and the string goes slack, or when a particle is on a surface and it leaves the surface, remember that our velocity is always tangential to the acceleration towards the center. That's a really important idea. So if I can get the velocity at that point, I know its direction, and I can treat this as the projectile that it's acting as. So the first thing we're going to do here is we're going to get our velocity as it leaves, or as the tension disappears, as the string becomes slack, basically at position B. So at position B, we know that cos theta is equal to a third. I have my formula for v squared, and effectively I can sub that in. So we get v squared is equal to gd 1 minus 2 cos theta. I can put in, instead of cos theta, a third, so 1 minus 2 thirds, and effectively we get v is equal to root gd over 3. So that is my velocity at point B. Now, the way that this is moving, because the string goes slack, it's now going to be acting under gravity. It's going to act like a projectile because there's no tension pulling it along. So here is my velocity at that point, just to go slack. So think about this as my horizontal line, and I can actually show that this angle here is theta. Now, that might be tricky to think about, but if you see, we have a theta here. So imagine here's my right angle triangle we have there, and we have theta. Okay, so then here it must be 90 minus theta. So this angle here is 90 minus theta. And because this velocity is tangential to the radius, this whole thing is 90 degrees, meaning if this part is 90 minus theta, this bit must be theta. So effectively what we have, let me actually just draw it down here so I can make it bigger. So we have a line here that's effectively making a right angle. So if this is theta, this is 90 minus theta, and then this one here must then be 90 minus theta, which is just going to give us back to theta. So that angle there is theta. So when you're working it through, you might go, God, I have no idea how to get that angle, but really think about that right angle that we have in here, and it will help. So I can leave that in if it's going to be helpful. So we have our angle here is theta. So effectively we have a projectile. So when we're dealing with our projectile, we think of our new initial velocity as, I'm calling this v, I know it should be u, but v because this is what I've worked out over here. So it's the magnitude of v cos theta, magnitude of v sine theta. Because I'm moving to the left and up, I put the I as a negative and the j as a positive. And for us, that idea of the magnitude of it, the size of it, it is just v. So this piece here, this is root gd over 3. So we're asked to get greatest height. So that is effectively find sy when vy equals 0. Now it says above b. So that that horizontal red line I've drawn in, that is our baseline, and that's literally just going to give us our answer. We don't need to do any kind of adding on when we get that. So I'm only working in a y or j direction. So I'm going to use this formula here. V squared is equal to u squared plus 2as. But we're saying we want to basically find s when v is 0. So I can literally rearrange this into s is equal to u squared over minus 2a. Because remember, v is 0. And this is only working in a j or a y direction. So it becomes root gd over 3 sine theta, all to be squared, all over minus 2. And our acceleration for in a y direction is always minus gravity when we're dealing with projectiles. So we can do a little bit of cleanup on this, but you might be going, oh, I don't know what sine theta is. Now, you can work out your angle and plug it back in, but that's not how we work in applied maths. So instead, what I'm going to do is I'm going to draw a little right angle triangle. I'm going to put in my theta, and I know cos, which means I know my adjacent and I know my hypotenuse. That's 1 and 3, which means that the opposite side now must be root 8. So that is 3 squared minus 1 squared, and the square root of that, which gives us sine theta, or sorry, sine theta is equal to root 8 over 3. So when I plug that in, I get, I've just separated this out, root GD over 3, and I'm going to square that, and then the sine theta is going to be squared, so that's root 8 over 3 squared, all over 2G. Bit of a pain that you can't put this into the calculator, but actually it's not going to be too awful, because that first bracket we have a square and a square root, which undoes each other. Root 8 over 3 all to be squared is going to give us 8 over 9. So we end up with GD over 3, 8 over 9, and 2G. There's a gravity on the bottom and a gravity on the top. And then we can do a little bit of work on it. So we get D by 8, so that's 8D over 27. So I'm just going to bring it here for a second. So I get 8D over 27, and that's effectively divided by 2. So that's going to give us final answer 4D over 27. So thinking about this and kind of getting it set up feels like it's very, very complicated. It is a tricky part. It is most definitely a tricky part, but you just need to bear in mind how once the particle is no longer on a surface, or once the tension is gone, so when reaction and tension are gone, effectively it's acting as a projectile, and that velocity is always perpendicular to the acceleration. It's always going to be perpendicular to the radius. It's going to be perpendicular to the centripetal acceleration, and we can show that using vectors. We can show that using some differentiation. There's some nice questions on that. But if you can remember that that velocity is always tangential to the radius, it's going to just help you make sense of how you can approach this add-on question. This question is from the 2024 higher level paper, and it's question 4. A snowboarder of mass m is traveling with the velocity v1 when he enters circular arc AB at point A. And we can see that in the diagram on the right. AB has radius 6.7 meters and center C. A, B, and C lie in a vertical plane. And AC is vertical, BC is horizontal. A student models the motion of the snowboarder, ignoring the effects of friction and air resistance. So part 1 asks us to draw a diagram to show the forces acting on the snowboarder when he is at point D, where CD makes an angle of alpha with the downward vertical. So just focus on what we're told. So D is here along the arc. So we'll start with our snowboarder, and weight is always a great force to put in first. We always know it works straight down, so our weight is equal to mass times gravity. The only other force acting on the snowboarder is the reaction, since the snowboarder is on the ground. The ground is curved. However, the reaction is always perpendicular to the ground, so it's going to come out like this. So here is my reaction, which we're going to call R. Remember that we were told that this is a circular arc, which means we have centripetal acceleration towards the center. So that is our acceleration there. And just to think about that angle, we'll need it for resolving. We don't need to resolve to get our marks for just the force diagram. What we have here is absolutely sufficient, but just for ourselves, it's handy to know that we can add in the angle here against the vertical. Be so careful. Really think about it in terms of the bigger diagram, if that helps. If we put a vertical line there, we have that lovely Z shape of alternate angles, and there is my alpha. So just pay really close attention to where that angle is going in, especially when we're dealing with circular motion, because often it's not in the most obvious place. So part 2 then says express the reaction force of the snowboarder at point D in terms of m, v1, and alpha. So what we're dealing with here is vertical circular motion. And what's really nice about vertical circular motion questions, although they can be quite challenging, we always approach them the exact same way. So now we're going to follow those 3 steps. So basically, step 1, we're going to resolve weight. Step 2, we're going to use the conservation of energy. Step 3, we're going to use F equals ma. So what we're going to do, we're going to take our force diagram that's there on the right that we had in the last part, and we're going to resolve weight. And that's so important. And a really common mistake students make is they resolve our reaction. So really focus on the direction, and it's so important when you're doing a force diagram to put in that direction, which is in red there with our A, and that's where we want all our vectors to either be parallel or perpendicular to A. So W is the one we need to resolve. So here's our force, and firstly we have weight. So this is mg acting straight down. We then have our reaction force, which is up here, and we have our acceleration pointing inwards. So we want to resolve our weight, our mg. So what we're going to do, we're going to draw in parallel and perpendicular vectors to mg, and I'm going to put in our angle to the vertical. And if you want to go back to your original diagram and think about, let me put it in a different color. So we're going to resolve weight here and here. And if you figure with the alpha, we have vertically opposite angles. That's where our alpha is going. So use your original diagram to help you figure out where the angle is going. That means we have here mg cos alpha, and this side is mg sine alpha. So the adjacent side is always cos, the opposite side is always sine. So we end up with our resolved vector is looking like this. We have mg in a different color, which will suffice for the exam as seeing it as not double counted. However, if you want, you can take that out. So just make sure it's distinguished, or what you can do is you can like put a line through it to show that you've already dealt with it. But like I said, different color should be absolutely fine. So step 1, done. We've resolved our weight. Step 2, so this is equation 1. So we have the conservation of energy. So the energy that's potential plus the energy that's kinetic at the start should be equal to the potential plus the kinetic at the end. So we're talking about D, and we're going to start at A. So these are our these are 2 points, A and D. So we want the first part, we're talking about at point A, and here we want at point D. So potential energy at A, so that's mgh. There is no height, it's at the lowest it can go, so we're going to put in a 0 for that. And that is equal to, that is plus kinetic energy at half v, and the velocity is v1, and that's squared. So then we have the potential at D. Now we need to think about, well, how high is this? So we have a few different ways we can think about it. So the total height here is 6.7. So the length from A to C is 6.7. And we can work out this little part of the triangle because we have our alpha. So this here is 6.7 cos alpha. So we can write that in terms of alpha, which is what we want. So we can say this piece here is the 6.7 take away 6.7 cos alpha. So that gives us mg, and our height 6.7 minus 6.7 cos alpha plus kinetic energy a half. We want this in terms of our velocity, v1, but it doesn't mention anything about the velocity here, so I'm just going to use this as v2, so our velocity, and that's squared. So we can get rid of this. Everything else has an m, and we can get rid of the half as well. So we get v1 squared is equal to 2g 6.7 minus 6.7 cos alpha plus v2 squared. So v2 is at D. So not a lot I can do with that at the moment. So we go to the second equation. So that's my conservation of energy. And then I do F equals ma. Remember, we're always looking at the direction of motion. The direction is given in our diagram. Really good habit to put that in anytime you're doing a force diagram. So what is pulling it to or with that direction? That's going to be or. Pulling it against is the mg cos alpha, and that is m times a. Now, we have two different options for our acceleration because it's an centripetal acceleration. We have v squared over or omega or omega squared or. So either or. Think about the question. We have nothing about omega or our angular velocity here, so that's not going to be the one we're going to use. We're going to use v squared over or. So that's v squared. Now our v is the velocity at point D because that's where we're doing the forces for. So that is v2 squared all over our radius, or we know our radius is 6.7, so if you want to put that in straight away, that's absolutely fine. So there are two equations. So we want to have the reactionary force, which we do, in terms of m, which we have v1 and alpha. The problem at the moment is the velocity 2, that v2. They didn't ask us for that, and they don't want that in there. So that's why we're going to use our two equations. We're going to isolate our v2 in equation 1, and then sub that into equation 2, and figure an isolator or to get exactly what we want. So just clearing the screen to give us a little bit more space. So I'm actually going to leave the square here because we're gonna need that when we sub it back in. So this becomes v1 squared minus 2g 6.7 minus 6.7 cos alpha. Plugging that in, we get or equals. I'm going to bring this across, so I get mg cos alpha plus m times all of this, so v1 squared minus 2g 6.7 minus 6.7 cos alpha all over 6.7. So this is effectively our answer, but we just want to do a little bit of cleanup on it. So we're going to leave that first piece as it is, cos alpha, and I'm going to break up the second fraction. So I get mv1 squared over 6.7 minus 2mg all over 6.7, 6.7 minus 6.7 cos alpha. Now we can see in the second fraction that tidies up a little bit for us. So we end up with mg cos alpha plus mv1 squared over 6.7. And this multiplies out to give me 2mg times 1, which is 2mg, and then minus, by a minus plus, 2mg cos alpha. You can multiply out those 6.7s and then divide in that 6.7 from the denominator, whatever way works best for you. Our reaction then is 3mg cos alpha minus 2mg plus mv1 squared over 6.7. Cleanup is not hugely important here. It's just nice to bring together those mg cos alphas because they do tidy up nicely. So we're then told that the snowboarder reaches point B with vertical velocity v2. So we're at this point here, and we have vertical velocity, so straight up, and that's going to be v2. So we had horizontal velocity there at the bottom and vertical velocity here at B. So we're trying to express v2 in terms of v1. So we're going to use the conservation of energy, similar to what we did in the last part, but we're using different points. So when we have the energy at A, so at A, we have potential plus kinetic, and that should equal the potential plus the kinetic at point B. So here we have the potential at A is going to be mg, and there is no height. It's at as the lowest point it can have. And then we have a half v1 squared. We have the potential at B, which is mg, and the height is going to be 6.7. It's just that vertical height, plus a half and v2 squared. Now, don't be worried too much about that idea of horizontal versus vertical velocity. How do we deal with that? When we deal with energy, energy is a scalar, which means direction doesn't matter. So when we talk about half mv squared, that v actually stands for speed. So all we put in is the actual magnitude. We don't care about like the direction, the sign, or anything like that. So it is absolutely fine to put in exactly as we have here. So it's really, really important to understand the difference between vectors and scalars, the impact it has with regards using formula. And it's really important to understand when like energy, for example, is scalar, work is scalar versus velocity being vector. It's really important to know that. So this goes to 0. We have the m's disappearing. We want to write v2 in terms of v1. So we're going to multiply across by 2. So we got v1 squared minus 6.7 g is equal to, sorry, I've lost my 2 there. So it should be minus 2g times 6.7. We'll multiply that out in a sec. And we have v2 squared. So v2 is going to be the square root of, we have v1 squared minus 13.4 gravity. Or if you want to put that in as 9.8, that's absolutely fine.